Diagnosing vehicle faults is only as hard as you make it, so it's a great idea to arm yourself with some quality diagnostic equipment. An oscilloscope is an essential tool for the modern workshop. Using other equipment such as a Noid light or spark tester when looking for a fault only presents half the story. The best tool to use for voltage or current monitoring is an oscilloscope. It can provide electrical signal data, which is vital when trying to diagnose a fault. When presented with a misfire, the scope can reduce the amount of time needed to isolate the fault to a system, whether it be compression, ignition, or fuel. This is a big plus, as older model vehicles don't have the ability to log misfire-related fault codes that are normally found using a scan tool. Traditionally, the first check we would perform is a compression test. Unfortunately, this is not always feasible due to the engine design, construction, and especially when the vehicle has just been driven for the past hour. The last thing we wanted to do is remove the spark plugs to perform a compression test, as this could cause damage to the cylinder head. A lot of manufacturers recommend not to remove the spark plugs until the engine drops to a set temperature. So, let's perform a compression test with the oscilloscope. Although this isn't as accurate as a mechanical gauge, the outcome of this test will determine what the next step in our diagnosis will be. Again, I can't stress how important it is to use a battery maintainer. It's critical to ensure a stable voltage when performing these tests. As you can see by our results, the mechanical side appears to be okay. If there was a problem here, we would need to use a mechanical compression gauge and retest all cylinders the old-fashioned way. The next step is to check the ignition side. This can be done with a coil-over plug tester. With the vehicle running, rest the probe over each coil pack while watching the display. A correctly operating secondary coil trace will look like this. In this section of the trace, the pattern reflects the primary side coil saturation time. The peak voltage seen here is what's needed to overcome the plug air gap resistance. With the engine at idle, the voltage should be around 10,000 volts. A lean mixture requires a higher firing voltage to jump the air gap, while a rich mixture would use less. If the firing voltage was dramatically reduced or non-existent, there could be tracking down the plug or lead, arcing to ground. The next section of the trace is the burn time. This shows a period of time that the spark is jumping the plug gap. Coil oscillations occur directly after the burn time has ended. This is because there is still some energy left in the ignition coil, but not enough to continue the spark event. This residual energy dissipates to ground. We can see by our secondary pattern that the ignition system is operating correctly. The next step would be to look at the fuel system and test the ECM's control of the injectors. At this point, checking with an oscilloscope is faster than connecting a fuel pressure and flow gauge. This scope has 4 channels, so it's good practice to connect and observe all injector patterns at once. Back probe each injector control side and connect the ground lead to battery negative. If you are unsure which is the control side, refer to the vehicle's fuel delivery schematic for the correct pin location. Because we're using the Oscilloscope 4425, we'll use the quick setup menu and navigate to the injector test. If you are using a different scope, some setup parameters to use would be a voltage range of plus or minus 100 with a time base of 2 milliseconds. With the ignition on, we should see battery voltage displayed. In this instance, our trace will reflect the battery maintainer's output voltage. This confirms the supply relay, harness, and injector windings are free from opens, shorts, and excess resistance. If we saw 0 volts here, move the scope lead to the supply side and recheck the trace. If battery voltage is now established, then there is an open within the injector windings or harness connector. So, this would be the cause of our misfire. If battery voltage still isn't seen, there is an open between the injector supply terminal and the EFI relay. 0 volts may also mean a short to ground in the supply circuit, but that would cause a no start symptom and would open the circuit protection device. Let's move the back probe to the control side and observe what an excess resistance in the circuit would look like. With the ignition on, anything substantially lower than battery voltage would indicate excess resistance. We can now move the probe to the supply side while watching the trace. If battery voltage is seen, there is excess resistance in the injector coil windings or harness connector. If the voltage remains the same, the excess resistance would be in the supply side and require further diagnosis of the EFI relay, connectors and harness. Let's move the probe back to the control side and start the vehicle. Before we compare all four traces, let's take a closer look at a correctly operating single injector trace and break it down into three sections. Pulse width is the time the injector is held open. This is when the ECM grounds the control circuit. We can see the pulse width is around 2 milliseconds at idle. When the ECM grounds the injector, a magnetic field is produced by the windings. This magnetic field is what lifts the pintle off its seat. When the ECM opens the driver's circuit to close the injector, the magnetic field collapses across the injector windings, inducing the current flow in the circuit. This is back EMF. It's very similar in operation to an ignition coil. Back EMF levels can reach around 100 volts. This section displays the circuit voltage when the ECM driver is in an open state. The voltage should always reflect that of the alternator's output. Let's go back and look at all four injector traces on the scope. We can see that cylinder 2 is displaying battery voltage with no ECM driver input. This would mean there is an open in the control circuit. This could be located in the harness, connectors, or ECM. To help isolate the open, we will need to turn off all other channels and focus on cylinder 2. Using a second channel, back probe injector 2 control terminal in the ECM connector. Connect the ground lead to battery positive. We connect to battery positive because the ECM uses a low side driver to control the injector operation. If the voltage trace on the second channel looks like this, then there is an open between the two connectors. On channel 2, we can see the open circuit voltage pulled to ground by the low side driver. This confirms the ECM control is operating as designed. Therefore, the open must be between the two connectors. If the voltage trace remained the same as channel 1, then the fault would be internal to the ECM. A short to voltage in the injector control circuit will also cause an engine misfire. The engine needs to be running for this to show on the trace. A short to voltage will look like this. The ECM cannot trigger the injector when the voltage is held high. To isolate the short, turn the ignition off and disconnect the injector. With the scope still attached to the control side of the connector, turn the ignition on and watch the trace. If the trace drops to 0, the short will be in the injector assembly. If the voltage remained high, turn the ignition off and disconnect the ECM. Turn the ignition back on and watch the display. If the voltage disappeared when doing this, the short is in the ECM. If the trace remained high with the ECM disconnected, then the short to voltage will be in the harness between the two connectors. Excess resistance in the control side will also cause an engine misfire. Excess resistance in the circuit will look like this. If we compare this with a good trace, we can see the pulse width section ramps up much earlier than expected. Due to the excess resistance, there isn't enough current to create the magnetic field required to lift the pintle off its seat. This is confirmed when looking at the back EMF spike. It is much lower than it should be. Using the scope to locate the excess resistance is easy. To isolate the excess resistance to either injector, harness or ECM, move the ground lead to battery positive and disconnect the injector. Observing the trace, the ramp has disappeared, indicating the excess resistance is in the injector. If the trace still looks like this, the excess resistance will be in the harness or the ECM itself. To identify which of the two the excess resistance is in, connect a second channel with the ground lead connected to battery positive and the other back probed at the ECM connector. Run the vehicle while monitoring the trace. If the excess resistance is within the harness, this will be evident when comparing the two patterns. We can see the triggered point on channel A isn't pulled as low as channel B. This indicates that there is excessive resistance in the harness. If the pattern was identical with both channels connected, this would indicate excess resistance in the ECM connector or the ECM itself. Perform a terminal tension check and corrosion inspection of the ECM connector and pins. If this is okay, the fault will be in the ECM. Well, there you have it. We've just performed some in-depth injector circuit diagnosis without the use of a scan tool, multimeter or test lamp. Using an oscilloscope as part of your diagnostic arsenal will make you more confident with fault finding and system repair. Thanks for watching. See you soon.